All right. Hello, everyone, and welcome back to another Qubit by Qubit lab. Hope your week was a good one. I hope that the homework wasn't too bad last week. As usual, we will be going over everything again in just a few minutes, but this week's main topic is going to be on probability and random variables. So as you may have picked up by now, a lot of stuff in quantum computing, most notably superposition, involves things that are sort of inherently random, right? When we say something is in a superposition of 0 and 1, we mean that there's a random chance whether you end up with a 0 or 1. And so the study of probability and these things called random variables, which we're going to get into today, is a very central part of quantum computing theory and will be important going forward in the course. So without further ado, let's get into things. The agenda for today looks pretty similar to most agendas. We have a small logistics / announcement thing right at the beginning. Then we will do our normal Canvas attendance quiz. And then we will get into the main content of the lab, starting off with the pre-lab Zoom feedback, questions from last week, the lab content on probability and random variables, and finally, post-lab Zoom feedback. So first up, announcement. This is, I guess, just a reminder. It's not actually a new thing, but this is just a reminder that Piazza is available for you to use. It is a great resource for content-related questions. I'm pretty sure I've mentioned it sort of in passing at just about every lab that you can always ask questions on Piazza if if we don't have time to get to your question here in the lab session, or if you just don't feel comfortable asking your question in the lab session. You can post on Piazza, you can post anonymously if you would like to, and there are a whole bunch of very helpful students and TAs on Piazza who are more than willing to help answer your questions. So you can post questions from lectures, labs, homework, or anything else. If it's not super related to lab content, it might take us a bit longer to answer, but really post anything you'd like on Piazza. Responses are from instructors, TAs, and fellow students, as I said. Right now, we're sitting at an average response time of about 15 minutes. So apparently it's really, really fast. When you do post something on Piazza, someone will get back to you very quickly. I know TAs, like we try and check it at least every day. So you should get sort of a quote unquote official response from the instructing staff at least within a day. But from fellow students, responses can sometimes come a lot faster. If you have not been able to access Piazza for the past couple of weeks, for whatever reason, go ahead and email student@qubitbyqubit.org, and they should be able to sort out getting you onto Piazza. It's definitely a very useful resource to have. I guess just one final note, even if you don't intend to use Piazza in the near future, just log on and check to make sure that you can use it, you can access it. I know for my personal school, when we use Piazza for our courses, oftentimes the times I need it most is sort of when I least expect it, when I'm struggling with a particular homework question or something. It's good to just know how to log on, how to post a question, because you never know when you might need a bit of support. Okay, that's our announcement for this week. So let's go on and do the Canvas attendance quiz as usual. So lab number, as you know by now, is 2A. The quiz password is 3308, which is the same password that's in the bottom right of the screen. The question this week is a little bit different from the ones we've had previously. Again, as you can probably realize, we're sort of figuring out what works best as we go along. And so this week's quiz is meant to give us a sense of how long you're taking to do the homework. And we will use this to sort of gauge how difficult the homework has been relative to everyone's level of understanding. So you're given a few choices. Either the homework takes you less than an hour, 1 to 2 hours, 2 to 3 hours, or more than 3 hours, or I guess you didn't do the homework. So clearly this kind of question is not graded, but it does, as usual, count for attendance. So make sure you log on to Canvas, fill in an answer for this, and it really should help us gain a better understanding for how well the homework is matching sort of what we think it should be. Okay, I will also turn on the chat here in case anybody has questions. You can go ahead and throw those in the chat, but otherwise I'll wait just 30 seconds or so for everyone to fill in the Canvas attendance quiz, and then we'll get on with the rest of the lab. Okay, so seeing no questions in the chat, I'm hoping that maybe Canvas is finally totally figured out for everyone, which would be amazing. Once again, though, if you do have any problems, feel free to throw them in the chat, or as always, you can email student@Qubit by Qubit to get help with any of these sort of administrative details. Okay, let's launch into the pre-lab Zoom feedback. So you should see a poll on your screen right now that's asking for how well you understood this week's content. And I'd like everybody to sort of do the same thing as last week. Actually, I forget if I did it with this group or not, but if you could just throw in the chat if there were any specific ideas that seemed unclear that you think we should spend more time on in this lab. Just as a quick refresher, some of the things we'll be going over is probability, random variables, expectation and variance, and then Brockett or Dirac notation. So those are some of the main themes we'll be covering. If any of those were particularly confusing, go ahead and throw it in the chat and I will be sure to spend a bit more time on them. Otherwise, we'll just kind of do a sort of even covering of all of the material. Okay, so thank you everyone for filling that out. We have one vote for Dirac notation in the chat, perfect. So that's gonna come right at the end of the lab. And so I will try and make sure we have lots of time to get to that. Repeat what I said, yeah, so just the main topics for this week's lab are going to be probability, random variables, expectation variance, and Brockett or Dirac notation. And so if any of those are particularly confusing to anybody, throw it in the chat and I will do my best to accommodate and go over them a little bit more carefully. Awesome. Okay, so as I pretty much just said, main topics for today. First, we'll spend quite a bit of time talking about probability, which encompasses a whole bunch of different things. Events and normalization, random variables, probability mass function, expectation variance. We'll spend just a little bit of time talking about joint probability, and we'll explain what that is when we get there. And then finally, relating probability to quantum computing. So going over Brockett notation, and as usual, I will be going over the optional content in today's lab, even if we do have to go over time. Okay, before we get into this week's content though, let's talk about some questions from last week. First one was about whether complex numbers are scalars. So this is a pretty natural question, I think, because for all of the time we were teaching complex numbers, we were telling you to visualize it on a coordinate plane, right? We had our imaginary axis in the vertical direction, real axis in the horizontal direction, and we told you to picture complex numbers as being points on this plane. And those points definitely kind of look like vectors, and we talked a lot about how complex numbers were similar to vectors. However, for purposes in mathematics, and when we use the terms vectors and scalars, complex numbers are classified as scalar numbers. And so the reason for this is you can kind of think about the operations you can do with complex numbers, right? If I have a complex number, say Z, Z1 and Z2, I can do pretty much all the things that I would normally do with numbers with these two complex numbers. I can add them, I can subtract them, I can multiply them, I can divide them. We learned other stuff too. But these numbers are just scalars. So all of these operations work in some way on complex numbers. However, if you look at vectors, right, if we have vectors v and w, for example, well, you can add vectors v and w. You can actually subtract them, even though we didn't exactly go over that. You can kind of multiply them. That's sort of like what inner product is. Dividing, we didn't really have a notion for this. And so you can already see that the operations you do on vectors are very different from complex numbers. And so for this purpose, we classify complex numbers as scalars. I'm not going to spend too much more time on this because it's kind of just a technicality that, when we talk about scalar and vector numbers, complex numbers are always going to be scalars. There is a pretty interesting and deeper mathematical argument for why this should be the case. And you're more than welcome to look that up on your own if you'd like. But the basic message here is, if we haven't been clear enough in the past, complex numbers are scalars. They always will be for this course. So that's just, hopefully that clears that up. Second question from last week. Why do we take the transpose of one vector for inner product? So before I answer that, let's just refresh ourselves on what that even means. Last week, we learned about the inner product between two vectors, v and w, and we learned that it was written something like that. And in the definition, we saw that this was sort of defined as v dagger, we introduced this new dagger symbol, times w. Now, say that v, I'm just gonna come up with some random vector here. Let's say that v is, say, 2 plus 5i and 1 minus I, so it has some complex numbers in there. We learned that v dagger is obtained by taking the conjugate and then the transpose. So v dagger would be equal to, first I conjugate everything, 2 minus 5i, conjugate the bottom, 1 plus I, and then I take the transpose of that. And all the transpose meant was flipping rows to columns and columns to rows. So here we have a column, we're gonna flip it to a row. Just like that. And that is what v dagger would be. So the question here that we heard a lot was the conjugation part. This makes sense. That changes the values inside the vector. So that could be important. But why does this last step really matter? Why do we care so much about switching columns to rows and rows to columns? So hopefully I will try and answer that right now. The answer is what we'll call dimensional consistency. And I think the best way to show this is, again, through just an example. Suppose we have these two vectors. Again, these ones just have real numbers, so the conjugate part won't matter. If I take the inner product of w and v, this is just going to be equal to w dagger v by the definition of inner product. And then because w just has real numbers in it, conjugation doesn't do anything. And so dagger basically just means do the transpose, like this. Now, let's write out what the dimensions of each of these are. Our first quantity here has 1 row and 2 columns, so it's 1 by 2. The second one has 2 rows and 1 column, so it's 2 by 1. And what you'll notice is that when we write it this way, the inner dimensions match, which is the same rule we learned about last week when we were looking at matrix multiplication. If, on the other hand, we had not done the transpose and we had just written w times v, which is incorrect, but just to sort of illustrate this example, you would have had 3, 2, which is w, 2, 1, which is v. And again, if we write out the dimensions here, we have a 2 by 1 and a 2 by 1. But the problem is that these inner dimensions no longer match. So the whole reason we do this transpose operation on that first vector is purely just so we can get these dimensions to match in the middle. And that's the same rule, right? Here's that same example again. We get the inner dimensions to match. It's the same rule we had for matrices, right? So here we have a matrix. Now we have 2 rows and 2 columns, but still we have that same rule where the inner dimensions have to match. It doesn't matter if you only have 1 row or 2 rows. You could even have 3 rows. The same rule still holds. These middle 2 numbers must always match. And so making sure that those middle numbers match is really the reason we do transpose in the inner product. Okay, so that brings us to the end of last week's, I guess, questions. So we'll dive into probability, which is this week's main piece of content. So the first point here is that quantum mechanics, and therefore quantum computing, is inherently probabilistic. And all we mean by inherently, this is a little bit of a technicality, but it's important enough that we think we should teach it. It's not the same as things in your regular day-to-day life that you might think of as being random. So for example, if you flip a coin, you probably think that it's about random whether the coin lands on heads or tails. But very technically speaking, if you had perfect measurement instruments that could tell, exactly how heavy the coin was, exactly how it was being flipped, how its momentum would change midair, how all the air currents in the room would push it around, et cetera, you could, in theory, calculate whether the coin would land on the heads or the tails, right? So it's not random because there's anything inherently random about it. It's just that we don't know enough about the coin or the air in the room or how it's flipped to make an accurate prediction. So the outcome appears to be random. Quantum mechanics, and therefore quantum computing, are different. Even if we had perfect instrumentation that could measure everything exactly as precisely as is possible, you would still see randomness. So quantum computing is random, not just because we don't fully understand the problem or we don't fully understand the physics of what's going on. We do fully understand the physics, but the physics actually tells us that the process will always be random. So don't worry too much about this. It is a technicality. We're not going to ask you questions about it probably, but it is just something to remember that to get quantum computing and all the effects we're talking about here, you don't just need things that look random, you need things that are inherently, physically, by the laws of nature, random. And that's what quantum mechanics gives us. With all this talk about randomness, it would be good to talk a bit about how mathematicians and mathematics handles the concept of randomness. Before we do that though, I'll just do a quick, I don't know, informal chat poll. If people can just throw in the chat, where are some places where you see probability or randomness in your daily life? So I already gave one example, just like flipping a coin. Can anybody else think of examples of where you might see probability in your everyday life? So weather, yeah, absolutely. Weather is another one where this oftentimes appears very random. Stock markets, yes. Casinos, rolling die, exactly. We're actually going to come up with the dice example in just a moment. Yeah, so those are all perfect examples of probability. And we are actually going to take one of those examples, the dice, your school deciding what to do. Uh-oh. We're going to take the rolling dice example as the one that we talk about, just to introduce the concept of randomness and probability and go forward from there. So this is going to start off basic, and I'll go a little bit faster through this part. Consider a six-sided die. Hopefully everyone is familiar with this kind of thing. You can roll any number on the die between 1 and 6, and the probability of doing each of those things is equal. So what exactly do we mean by probability in this case? Let's write out some what I hope are fairly obvious rules for probability. The first rule of probability is that probabilities must be non-negative, right? I can say that there is a 30% of it raining tomorrow. It doesn't make sense for me to say that there is a negative 30% chance that it's going to rain tomorrow. So probabilities in quantum mechanics, just like in everything else, are always going to be non-negative. The second one that again should be fairly obvious is called normalization. Maybe that's well, actually, you should recognize that term from a previous lecture, but we're just using it in a new context now. Normalization refers to the fact that the sum of the probabilities for all 6 sides of the die, or in any other case, all of the different outcomes you might expect, must be 1. So in this case, we would guess that a die has a probability 1/6 of being on any of its 6 sides. And we know that if you add up all 6 sides of the die, you should end up with an overall probability of 1. It wouldn't really make much sense if there was some other probability here, like 1/10, and you added all of these things up and you got an overall probability of 6/10, because then what happens in the other 40% of the time, right? Your probabilities should always add up to 1 or 100%. Let's go back to the die example. As I said before, we would expect that the probability of landing on any side of a die is 1/6. How do we get that number? Well, probabilities have to be non-negative, right? So it has to be a number between 0 and 1. The probabilities have to add up to 1. So if you add all of these numbers, you should get 1. And then from 2 slides ago, we had that the outcomes were all an equal chance of happening. So you just take that 100% probability, divide it by all 6 of your equal outcomes, equally likely outcomes, and you get the probability for each outcome, 1/6. So far, so good, I hope. All right, let's talk about a term that we sometimes use associated with probability. We have this term that is an event, and an event is just a possible outcome of an experiment. So there's actually kind of 2 new words here. There's event and experiment. So experiment is just some process that has a random outcome. All right, so it could be rolling a die, it could be the weather, it could be gambling, it could be your school deciding what to do. It's whatever process you're talking about that is random. The event is what happens on one particular instance of the experiment. So if I roll a die, an event would be, for example, rolling 1 or rolling 6. Let's take a look at some examples of these events. We'll start off with what we'll call event A. So just like everything else in math, we like to give things letters as names. So event A is defined as the outcome of rolling the die being 5. And then the question we're asked is, what is the probability of event A? The easiest way to solve this problem, I know it looks fairly easy right now, but we'll get to more complicated examples. I'm just going to go ahead and circle all of the rows that match what we're looking for. So event A is just asking whenever the outcome is 5. So it's only talking about that row. The probability of that row happening is just 1/6. So probability of event A is just 1/6. Let's go on to another example, event B. So here we define event B as the outcome being an odd number. So this time, it's not going to be just a single row. There's several rows that are possibilities here. We could have the outcome being 1. We could have the outcome being 3. We could have the outcome being 5. And in any of those cases, the die will have rolled an odd number. And so to get the probability of event B, we just add together all the probabilities. So that's 1/6 plus 1/6 plus 1/6, which is 3/6, which is half. So here the probability of event B is just half. It'll happen 50% of the time. All right, last example. For this one, I am actually going to get everybody here to try it on their own with a Zoom poll. So go ahead and use the same strategy that I just described, circling the rows that should count as a part of event C. Add up the probabilities and tell me what should the probability be for event C. How do you actually write the P? Oh yeah, good question. Max is correct here. So when you're handwriting it, the way that I normally like to do it is, if you just watch my screen for a second, you would normally write a P like that. Here you can just start off with 2 lines and then finish it off as a normal P. You'll see these sort of like double-lined letters a lot in math. Okay, so it looks like people are starting to fill in their answers for this question. So I'll start going through how I would do this. The outcome should be greater than 1 and less than 5. So what outcomes count as greater than 1 or less than 5? 2 is certainly greater than 1. 3 is greater than 1. 4 is greater than 1. And then it has to be less than 5. So 5 and 6 don't count. Therefore, the answer to this one is actually just the same as the probability of event B, which is just 1/2. Okay. Oh, follow-up question. How would you type it on a computer? So you can type it in an equation environment. So in Microsoft Word or PowerPoint or whatever, you can go to, I think it's like insert equation, and then you can start typing an equation. I don't know the exact command to do this, but you can look up how to do it online. Actually, I could even look it up and sort of send it out on Canvas, I believe. But it's in LaTeX, which is a software you can use to sort of write math. I believe this is called a mathcal letter. So you would use mathcal to sort of to type this letter P like this. That's totally kind of irrelevant, beyond the scope of this. But yeah, you can type it in the equation environment within PowerPoint or Word. Okay, so thanks everyone for filling out the poll. It looks like mostly people got it. I think the people who didn't get it probably just the greater than and less than terminology. You might have included 1 or 5. This was the answer we're looking for, but hopefully questions like this should always be very clear if we ask them to you. So let's look at our final example of an event, event D. Now, event D is defined as the outcome being greater than 1 and less than 5, so exactly what we just saw, or being an odd number. So that was event B, if you remember from the previous slide. What is the probability of event D? So I'm going to take this in pieces. First, I'll consider what rows count for the outcome being greater than 1 and less than 5. So that is the exact same as what I just drew. It could be 2, could be 3, or it could be 4. Now let's go ahead and circle the rows for the other part of this, or it's an odd number. So it could also be 1 in this case. It could be 3, or it also could be 5. And all of those count as event D happening. So by looking at this, we can use the same rule I just said, look at all the probabilities, add them up. We have 5 times 1/6, which gives us a probability of 5/6. Now, there is another way to do this. As I sort of alluded to, the 2 pieces of this question are events that we have already seen. So this first part, the outcome being greater than 1 and less than 5, that is just event C from the last slide. And if you remember, the probability of C that you filled in on the Zoom poll should have been 1/2. This part about it being an odd number, that is event B from the previous slide. And remember, we also had the probability of B was equal to 1/2. And so it might seem natural to say that because D is just B or C happening, that we would compute the probability of D as adding the probabilities of B and C. So if we work that out, we get 1/2 plus 1/2, which is 1. And clearly, 1 and 5/6, these are not the same thing. And in fact, it doesn't really make much sense for us to have gotten an answer of 1, because that means that event D would happen all the time. But clearly we can roll a 6. A 6 is not greater than 1 or less than 5. A 6 is not an odd number. So event D should not be happening with a probability of 1. So what happened here? A clue as to what happened is the fact that we circled this 3 row in both blue and black ink. It counted for both event C and event B. And so when we added for the probability of B and C, we effectively double counted this particular outcome. We accidentally added this probability of 1/6 of the 3 happening. We added it twice. So the correct way to do this is actually using a formula that looks like this. Sometimes you'll see this called the inclusion-exclusion principle. And all that it's saying is this little symbol here, it's not a big deal if you don't perfectly follow this. I just want to introduce the idea. This little symbol here is effectively or. So in this question, D, the event D, was equal to B or C happening. So in our example, we were looking at P of B or C, is what that little U symbol looks like. This is equal to, so it's going to tell us, we just follow the formula. P of the first thing, which is B, plus P of the second thing, which is C. But then it has this extra piece on the end, minus P of This symbol here is and. So it's asking us for the probability of B and C happening at the same time. And as I just alluded to, B and C happening at the same time, that only happens when we get a 3 as our roll. 3 is the only number that's greater than 1 and less than 5 and is an odd number, right? All of those things are true. So this last number here is 1/6. And the way we should have computed our probability is by taking P of B plus P of C minus 1/6. And if you work that out, that is indeed going to give you 5/6, which is the correct answer. All right, let's talk about the next topic in probability and randomness. This is going to be random variables. So we define a random variable x, and random variables, by the way, to distinguish them from a normal variable, we write them as a capital letter. So a random variable, capital X, it essentially just maps the outcome of an experiment, which remember is some process that has a random outcome. It maps the outcomes of the experiment to numbers. One way that I like to think about this, just as an easier way to remember, I like to think of random variables as being this like box. And every time you shake the box, a different number comes out the bottom. So you might have this random variable X, you would shake the box and you might get that a 4 pops out the bottom. But then if you shake the box again, you might get that 2 pops out the bottom this time. And if you shake the box again, you might get 4 again. It's totally random what comes out of this box. But that's how I like to think about random variables. It's a box, you shake it and a number comes out, but shaking it multiple times might give you different numbers. In the previous example of rolling die, we would say that if the dice rolls 4 for an experiment, then our random variable, capital X, equals 4 for that roll. So it takes the result of our experiment, the dice rolling 4, and it turns it into a number, which in this case is fairly straightforward. It's just whatever number was shown on the die. Another example, if the dice rolls 2 for an experiment, X equals 2. I think you get the idea. And if the dice rolls X, so note this is lowercase, it's just a normal variable, just like anywhere else in math. If the die rolls X for an experiment, then our random variable, capital X, is equal to the lowercase x. Just to drive this point home, you might notice something that at first looks a little bit weird. In this column, we say that x is equal to 4 in one case, and then right after that, we say that x is equal to 2. For a regular variable, these things don't make sense. You can't have a variable x that equals 4 and 2 at the same time. But for random variables, like I said, every time you shake that box, a different number comes out. So it makes perfect sense to say that sometimes capital X is 4, but some other times capital X might be 2 or 3 or 5 or anything else. This leads us to introduce something called the probability mass function, or PMF. You'll sometimes hear it called. So the PMF is really just a long and scary name for something that is quite straightforward. So I'm going to throw the definition up for the dice. This is the probability mass function. Sometimes we will write it as f, and then in the subscript, the random variable. So this thing here is our PMF. And the PMF is defined to just be the probability that our random variable equals whatever value was plugged into the function at the time you evaluate it. So here we have a pretty straightforward PMF. It basically just always equals 1/6. When you have x equals 1, 2, 3, 4, 5, 6, you get 1/6 out of the function. So this function works just like anything else you've seen. I can write fx of x, or sorry, I'll use an actual example here. I can write fx of 2, for example. That's going to be equal to 1/6 because we just look up whatever row that is. Now, if you're sitting there thinking to yourself that this looks like just another way to package up the table we had where outcomes are on one side and probabilities are on the other, You are exactly correct. The probability mass function is basically just a function that describes the table we had before. So why do we care about such a function? Well, usually we will use this to give ourselves a graph or a plot, and the plot will give us some information about the random variable we're studying. So here, this is what the plot of the PMF looks like for the dice rolling experiment. We have all 6 of our possible outcomes or events, and each one of them has a probability of occurring of 1/6. So all of them are at the same sort of level. And visually, this kind of plot shows you that there is an equal chance of being anywhere between 1 and 6. Now, if all of this seems fairly straightforward right now, I promise we will get to a more interesting example very soon. Let's talk briefly about expectation and variance though first. So expectation is basically just another word for average. When you hear statisticians talk about mathematics and statistics, they will use the word expectation. When normal people talk about average values, they just say the average or the mean of something. That's really all we're talking about here though. If I shook my little random variable x like infinitely many times, and I took the average of everything that came out, what would that number be? First of all, here's some notation. So the expectation value is denoted with another sort of double bar letter, just like the P that was asked about before. The expectation of x is also sometimes written with these angle brackets. So it looks sort of similar to inner product, you'll notice, except instead of vectors inside those angle brackets, now we have a random variable inside the angle brackets. And the expectation is defined as the sum over all possible outcomes. So these x values are possible outcomes of the outcome itself times the probability that it occurs. That's a bit of a mouthful, so let's actually do an example of this. Let's do the dice rolling example again. In that case, the expectation value of x, which again we can write with these angle brackets, is equal to the sum over all possibilities. So a die can be anywhere from 1 to 6. First possibility is 1. And then we multiply it by the probability that it occurs. So the probability of getting a 1 here is 1 in 6. And then we just keep adding. What's the second possibility? Well, the die could also be a 2, and that happens with probability 1/6. It could be a 3, that also happens with probability 1/6. And then I could keep going, but you have 4, 5, and then finally 6 times 1/6. And if you just go ahead and plug this into your calculator, you should get a value of 3.5. Just to drive this point home, what this value 3.5 actually means is if I took my random variable x and I shook the box 1,000 times, and I took the average of all 1,000 of those numbers, I would get an average of 3.5. So notice here, by the way, the die can never actually roll a 3.5, right? You're never going to roll the die and get a 3.5 exactly. But the average of, say, 1,000 or 10,000 or 1,000,000 rolls of the die, the average will be 3.5. Let's talk about variance again, or I guess here. So the variance is another metric you can have of the random variable x. But instead of measuring the average or the mean, it's going to measure how, quote unquote, spread out the different values of x are. Now, I think the best way to see this one is with an example. So I'm not going to try and explain what it is too much until the next slide. I'm just going to say how to calculate it for right now. Now, this formula looks quite complicated. So let's walk through it. The variance, there's no fancy like double V or anything. It's just written as var of x. So that's just a different notation. And it's defined as the expectation. So using our previous definition, it's defined as the expectation of this random variable. So how does this random variable work? Well, we already computed what the expectation of x is. That's 3.5. So this thing is really equal to the expectation of x minus 3.5 squared. So what this is asking us is now we have a box where every time we shake it, it effectively rolls a die, but then it subtracts the value of 3.5 from the die roll and squares it. And that's the number that comes out of the box. So we shake this box a whole bunch of times, and now we're asking what are the average of those values? What are the average, or what is the average when you subtract 3.5 and square all of your dice rolls? And it turns out that this is the formula for doing just that. It works the same way. We're summing over all possible outcomes x. So in the example of dice rolling, we would have that the variance of x is equal to, what's the first possibility? The first possibility is 1. So we would have, just using this formula up here, the x is the possibility, so 1, minus, remember we said the expectation of x is just 3.5, and then we square all of that. Then we always multiply by the probability of that happening, 1/6. Then the die can also roll a 2 minus 3.5 squared times 1/6, and so on and so on. If you work this out on your calculator, you'll get a variance of about 2.92. Now, again, I'm not going to try and explain what this number means too much, but we are going to jump to the next slide, and hopefully you'll start to get some sense. We've been talking this whole time about what we call a fair dice, a die that has an equal chance of landing on any of its 6 sides. But what if we had an unfair die? Here we're looking at the PMF, which remember, each bar here is just the probability of rolling that number. And for this particular die, there is a much bigger probability of rolling a 3. In fact, we're going to roll a 3 50% of the time. So someone has like attached an extra weight to the 3 face or something like that, so that when you roll this die, it's much more likely to come up as a 3 than any other number. So let's go ahead and compute the expectation and variance for this. Here's a reminder of what the expectation formula is. Remember, these x's are just all possible outcomes of whatever experiment we're looking at. So here, the experiment is just rolling the die. Here is our probability mass function, which remember is just a fancy way of saying it's the table that tells us the probability of every outcome. And now my question to you, and what will be the next Zoom poll, is what is the expectation of this unfair die? So I've opened up the poll. Go ahead and try this for yourself. Use this formula. Remember to sum across all possible values of the die roll, and then multiply each of those by the probability of that roll occurring. So I'll give some time for this because I know this is going to be, or I'm guessing anyway, this is going to be a harder problem. But really just take your time, try and remember what I did for the fair dice example, and see if you can work out what the expectation should be for yourself. I'll give about a minute here, and then I will go over the answer as well. Okay, so I'm just going to keep waiting a bit. It looks like people are taking longer to answer this question. I know there's a lot of calculation involved. So I'm just going to give maybe another 30 seconds and then I'll start doing the solution myself. Okay, so why don't we go through how to do this example? Now, like I said before, these x's that we're summing over are all of the possible outcomes of the die. For the unfair die, the outcomes are the exact same, actually, as the fair die. The only difference is the probability of them occurring. So for the expectation, I'm going to start off. I could have a 1 as my dice roll, but that does not happen with a 1/6 chance here. That happens with a 1/10 chance. So remember, if we look at our formula, the x is the outcome we're looking at, which in this case is rolling a 1. And then p, that our random variable equals x, is just the probability that rolling this die will give us a 1. And here we're told exactly what that is. It's 1/10. Let's go on to the second possible dice roll. We could roll a 2. What's the probability of a 2? Well, we're given that by our PMF. It's also 1/10. We could also roll a 3. And in this case, the probability is not 1/10. The probability of rolling a 3 is half. So we'll plug that in. And then all of the remaining outcomes are just probability 1/10. So we're going to have 4 times 1/10 plus 5 times 1/10 plus 6 times 1/10. So again, just to go over where I'm getting all of these numbers from, the first number that I'm multiplying is always a particular roll of the dice. So that's what the x in this formula represents. It's a particular outcome of our experiment. Then the second number I'm multiplying is the probability of getting that particular outcome. And that's the part that was different for the unfair die compared to the fair die. So this is the equation that you should have gotten just by taking all of the possible values of the dice roll multiplied with all of their probabilities. And if you work this out, I believe you should get 3.3 as the correct answer. So I will be pausing for questions very soon, I promise. But just to finish off this section, we do have one more slide. Oh yeah, I was going to mention as well. The variance you can work out in the same way. And the variance you would get here would be 1.81. It's a fairly long calculation, so I'm not going to do it here. But again, just remember that the x's you're summing over, those would be the exact same as the x's I summed over here. It's just all of the rolls from 1 to 6. This is what I wanted to show you. So these are the PMF plots for the fair and unfair die. This fair die one is the one that we saw in the previous, like a few slides ago. And it, as we expect, has every roll being the exact same. Moreover, when we calculated the average or the expectation, we found that it was 3.5. So the average is basically right there. And that kind of makes sense. Just by looking at this, that dotted line seems to be right in the middle of all of the probabilities of the die roll. Let's look at the unfair die now. So as we would expect, there's a much higher chance that you get a 3 on this unfair die, and then only a 1 in 10 chance of getting any of the other values. So here, as would be expected, the average is a little bit lower, because as you can see, the general, the distribution of probabilities here has shifted to the left. We've shifted some probability away from 4, 5, and 6 into 3. And so our average, instead of being 3.5, now it's going to be about 3.3. But the main point here is about variance. So before I sort of glanced over this and said, well, variance is a measure of how spread out the data is. Hopefully this is a good visual example of what that means. Here we can see that the variance of the fair die is greater than the variance of the unfair die. And the reason for that is that the probabilities here are more spread out. You can almost picture it as the plot being flatter. But over here, we have a very clear peak right in the middle of the plot. And so our probability is not as spread out. It's very focused on only one value. And so the more focused our probabilities are, the lower the variance. If our probabilities are very spread out over many possible outcomes, then you would expect the variance to be higher. And that's what we mean when we say the variance is a measure of how spread out your outcomes are. Okay, so that was a very long section. I apologize for that. I know we haven't paused in a while. So I am going to pause for questions here. I also realized that we're running short on time. So unfortunately, this week, I might go a little bit over time, even for the required content. But I do want to pause and give a lot of time for questions in case people still have any confusion or doubts about all the probability stuff I've discussed so far. So I see that there's a lot of stuff in the chat. I'm not going to go back and read all of that, but if you do have questions, please feel free to throw them in the chat now, and I will try to address them. Okay, so first question, in an unfair die, if the probability of 6 is higher than the others, will the average be higher than 3.5? Great question. So I'm going to go back to this slide and see if we can think about what the solution should be. So in the case you're describing, instead of having the spike on 3, say that we have our 3 has a 1/10 probability as well. Now you're saying that we would instead have a spike on the 6. So it looks something like that, right? And so here we can see that the probabilities, all of these bars, instead of being shifted more to the left, now we've shifted a bunch of them more to the right. And so indeed, the average or the expectation of the unfair die, if it was biased on the 6 instead of the 3, it would be higher than 3.5. Because again, sort of when you talk about expectation, it's kind of like where, I don't know if this will help, hopefully this doesn't make it more confusing, but it's kind of saying where is, like, if all of these bars were pieces of metal, where is the center of mass, right? So if this was like, some kind of table and I wanted to balance it on a point, where would I have to move the balance? So if I take a whole bunch of mass, I take a huge chunk of metal and I move it over to this side, I have to move my pivot point over to the right as well. So it's kind of like, it's the balancing point for the mass of all of the probabilities. That's why this thing is called the probability mass function, because when you draw it out like this, you can kind of think of it as being actual objects sitting on a scale. So next question, why does the probability change from 3.3 to 3.5 if the unfair die and the fair die still have combined to 1? Yeah, so good question. Our probabilities, as I said before, will always add up to 1. And the translation for that is basically when you roll a die, something has to happen. You're never going to roll the die and get, no answer, right? The average value, though, again, is sort of telling us where the balance is. Using that analogy of moving pieces of metal around on a piece of, on like a platform here, you can imagine that you always have the same amount of metal on top. You always have the same mass. the total mass is always 1. But if you move the mass around, you can change where the center of balance is for this panel. So I hope that sort of answers that question. But you're absolutely right that the probabilities will still add to 1. You have the same amount of metal sitting on top of your beam balance, but now you're going to start moving this metal to different parts of the balance, and that changes where the center of mass is. So lower variance means that data is less spread out. Exactly. High variance, more spread out. Low variance, less spread out. Okay, actually, so we just got final question I'm seeing here, or actually I'll answer one more, and then I will get back. Somebody asked me about probabilities of heads and tails. I will get to that in the next slide. So here someone says, let's say the only outcome was 3, the rest of the probabilities were 0, would the variance be 1? Or 0? Good question. I believe, I'm actually not sure off the top of my head. I think you would just have to go through and work it out with this formula. I guess it would be 0, right? The average of a die that just has 3 as the outcome, the average would be 3, because that's all of your mass is centered over 3. So your center of mass is on 3. And then the only possible outcome you have, you're saying, is a 3. So the variance in that case would just be equal to 3 minus 3 squared, which is 0. Okay, so why don't we move on for the time being? And I'm actually going to get to a question that was just sent in privately, but they were asking whether the expectation, or sorry, what would the expectation be for a coin toss, as an example, which doesn't have numbers for the values of x. So we're going to talk about that here. Before we do that, though, we're just going to go back and do a gentle introduction like we did before. Suppose we have a table, and now we have both a die and a coin, and we're going to flip the coin and roll the die. So clearly, the die can still land on any value from 1 through 6, but now we also have the coin, which can be either heads or tails. So now, instead of only 6 possibilities, we have 12 total things that could happen. Now, all of these have an equal chance of happening. So just like before, we would say that all of these have a 1 in 12 probability of occurring. So let's look at how we would represent this mathematically. Our random variable x is going to stay the exact same. It just maps the outcome of a dice roll to numbers. It's the same thing we saw before. But now, to the student's question, when we define our random variable y, it has to map the outcome of a coin toss to a number. It has to take as the input an outcome of the coin toss, and as an output, it always has to give you a number. So here, we're just going to arbitrarily define that heads is 0 and tails is 1. Just to illustrate and as an example, suppose we had that the die rolls a 4, for example, and the coin flips to heads. Then the values of our random variables, we would have x equals 4, just like before. But now y, we have to do this sort of translation from the actual experiment outcome to a number. So here we have that h corresponds to a 0. Now we could ask, how do you compute the probability of this occurring? Well, just like before, we saw we could ask, what is the probability that x equals 4 and y equals 0? And it turns out that as long as these are independent events, and all that means is that when I flip the coin, it doesn't affect the dice roll. It doesn't change the probabilities for the dice roll. The probability here is actually just going to be equal to the product of the probability of x being 4 and the probability of x being 4 and the probability of the coin being on heads, which again is y equals 0. So if we just think about this for a moment, we know from before the probability of the die rolling 4 is 1 in 6. And the probability of the coin flipping heads you can just think about this. It should be 1 over 2. And if we multiply those together, indeed, we do get 1 over 12, which is what we saw in the previous table. So let's do some examples with events again, just like before. The first one is asking, the outcome of the die is an even number and the coin gives heads. So I'm going to define these as two different events. We'll call the first one A1, which just corresponds to the die being an even number. And the second one, we'll call it A2, which is the coin flipping heads. And we're asked, what is the probability of event A? Well, that's equal to the probability of A1 and A2. And like before, I said, assuming these are independent, this is equal to the probability of A1 times the probability of A2. Now, if you think about for a moment, what should the probability of A1 be? So forget about the coin for a second, just go back to the die example. We did an example where we asked what the probability of rolling an odd number was. That turns out to be the same as the probability of rolling an even number, which is just 1 over 2. Now, the probability of getting heads when you flip the coin is just 1 over 2 as well. So the probability of this whole event happening is 1 over 4. Now, I encourage you as well, after the lab or something, you can go back to the table on the previous slide and circle all of the cells that this works for, and you'll see that 1/4 of the cells should be circled. Let's do another example. Same idea. We have a specification for what the die roll has to be. So for example, the die has to be less than 3. We'll call that B1. And the coin this time has to give us tails. That's B2. So whenever you get these sort of like compound statements, I like to label them with different event names. So here we have B1 and B2. So the probability of B is equal to probability of B1 and B2. And like I said, we just need to multiply. B1 times probability of B2. Now, again, you can work these out separately. For the outcome of the die to be less than 3, it can only be 1 or 2, so a 2 in 6 chance. And then the probability of flipping a tails is just 1 in 2. And so the overall probability here is going to be 1 in 6. And again, just like I said for event A, you can go back to the table, circle all of the cells where both of these things are true, and you should see that 1/6 of the cells are circled in that case. So to end off this example with the coin and the die, here is what the PMF would look like for this example. The way that we will often write it is just looking at X. So remember, X is a particular die roll. Y is a particular coin flip, where heads equals 0 and tails equals 1. So for example, if we look at this one right here, that's representing the probability of rolling a 2 and then flipping a tails on the coin. And as you would expect, all of these have a 1/12 probability. So I will pause here again for any questions about this whole topic, which is called joint random variables. So when you have two different random variables, you want to ask a question about the probability of two things happening, this and this. And we said that as long as those events were independent, you could multiply them together. So does anybody have questions about this content? Okay, so, actually, does it have to always be written that way on the graph's x-axis, or could it be written as 1, 0, then 1, 1? Right, yeah, good question. There's no common standard for this. So your axis would have to be, I guess, it would have to be labeled to tell you which order the two things happen in. But then how you order them on this axis, there's no obvious way to do it. So I would say there's no standard way. It could be written in the way you're indicating. Could this be used to find the probability of 2 qubits in a superposition? Yes. You're spoiling the last half of the lab, but yes, absolutely. That's exactly what we're going to get to. All right, cool. So if there's no other questions, the last part of the lab, oh, sorry, I'll answer one more question here. What would the probability be if you do 2 dice rolls and get 1? Because in the coin flip, you multiplied. So if you would multiply for the dice. Right. So if instead you had 2 die now, so before we had a die and a coin, now you're saying that we have 2 die, you can do the same thing. So if we wanted, for example, the probability of getting a 1 on both die, right? So that would be the probability, and let's just say that X is the random variable for the first die, Y is the random variable for the second. So you're asking for the probability that X is 1 and Y is 1. You're absolutely correct that you would just write this as the product of the probability that X is 1 and the probability that Y is 1, which in this case would be 1 in 6 and 1 in 6, which is 1 in 36. Now, things can get a little bit hairy here because this is the chance that your first die gives you a 1 and your second die gives you a 1. So if we had another example, like for example, P of X equals 1, and let's say we wanted our second die to be a 2, this would also give us 1 in 36, right? But this is only the chance that your first die gives you a 1 and your second die gives you a 2. So there is also a 1 in 36 chance that your first die gives you a 2 and your second die gives you a 1. So there's kind of like this ordering. You have to define one of the die as your first die and one of the die as your second die. That's the only way that this will work. Don't worry too much if you didn't follow that. I think the issue of having like multiple die is a slightly more complicated case, and we won't get into it. Okay, so let's charge ahead. I know I'm already over time, so I do apologize for that. We have a packed agenda today, I guess. So the final piece here is relating all of this probability stuff back to quantum computing. And the first thing we're going to do is introduce bra-ket notation. So I think the best way to do this is just show you examples, because at the end of the day, this is just a bunch of notation. So bra-ket notation, you've already seen some of it. Whenever we have a vector, a column vector, so for example, 0 with an arrow over top of it indicates a vector. We write it with this ket symbol around the 0. And in quantum computing, we always define the 0 vector, or sorry, ket 0, to be the vector 1, 0. Ket 1 is defined as the vector 0, 1. So this is just something that you kind of have to memorize, I guess, what these two definitions are. But the main point here is that an alternative way to write a vector is to write it as a ket. Now, when I introduced this before, you might have rightly wondered why we had this alternative way of writing vectors. Hopefully that will become clear now. Bra-ket notation, we've talked about what kets are. You might be wondering, okay, what's the first half of this? What are bras in this case? So bras are these symbols. They look very similar to kets, but they're sort of like flipped around, they're reversed. And it turns out that that is the symbol we use for the dagger of a vector. So just to relate this back to what we saw before, we talked a lot about V dagger as an example. Remember that you can write a vector instead of using an arrow over top. You can write it as a ket, dagger. And what we're saying now is actually the shorthand way of writing that is as what we call a bra, which just means you flip the ket symbol sort of 180 degrees, you flip it around, that becomes the daggered version of the vector. And what that means for our 0 and 1 vectors, because they are all real entries, the dagger conjugate does not do anything. So all the dagger is going to do is transpose, take columns to rows, rows to columns. And so we end up with these row vectors as our bras. Now, all of this is purely just notation. You just kind of have to remember, like I would say the things to remember. You should remember these two definitions and these two, which are obviously related, but those are the two that come up all the time in quantum computing. So why do we use bracket notation? Well, it turns out that it makes it very nice to write inner product. As a refresher, if we have the inner product of W and V, we're going to write that as W dagger V. As I said before, you can always rewrite a vector as a ket instead. And then when we have a ket with a dagger, we simply flip it around to get a bra, and those things are equal. And so you might notice that now we have these two notations for inner product that look very similar, right? Basically, the only difference is we stop drawing the arrows over top of the letters, and instead we put a bar in between them, and those two things are equal. So in quantum computing, to be completely honest, we almost never use this form for inner product. You will always write inner product like this, but they mean the exact same thing. It's the exact same math. All of the practice you've done with inner product before still applies. So let's have some practice with bracket notation and probability. As was mentioned before, vectors and therefore kets can be used to represent qubits. So in this case, our probability table looks like this. We have a 0, which as you remember is equal to 1, 0, or the other outcome is a 1, and both those things are equally likely. Probabilities have to be non-negative, they have to add up to 1, and so we get a 1/2 chance of each of those happening. Now, if I wanted to actually write out this vector, so I'll pronounce this ket psi, by the way, that's what that character is, ket psi. You might think that this would be equal to, actually, I think I have an animation for this. There we go. You might think that this is equal to the probability for 0 times 0 plus the probability for 1 times ket 1, right? That would make sense, but unfortunately, this is one of those very strange pieces of quantum mechanics that is not the case. It's similar, it's the right idea, but it's not quite correct. So it is true that you can write ket psi as a linear combination of ket 0 and ket 1, and we're just going to give these coefficients here names, alpha and beta. And in quantum computing and quantum mechanics in general, those coefficients are not exactly the probabilities, they are something else. They are, when you square them, you take the modulus, so these numbers could be complex numbers, you take the modulus, square the modulus, then you get the probability, right? So if I took alpha squared, that would give me 1/2, and if I took modulus beta squared, that would also give me 1/2. And so because alpha and beta are not exactly the probabilities, we actually have another name for them. These alpha and beta numbers are called probability amplitudes. So notice that second word there, amplitude. They're called probability amplitudes. So in quantum computing, whenever you write down a state, you're always going to be using the probability amplitude. And if we give you a homework assignment that has a state written down and you want to get the probabilities, you have to use these formulas here. You take the modulus and square it of all of the probability amplitudes. So we will do an example of this in just a moment, but before we get to that, I'm going to try and address the question of why this is the case. Why don't we just write it with the probabilities in front of ket 0 and ket 1? It turns out that this is for normalization. So what was normalization? Well, remember, normalization was the property that the probabilities should always add up to 1, which when we talked about rolling a die, that made a lot of sense. It turns out that in quantum computing, the same result expressing normalization is this. So it's basically saying the inner product of any vector with itself, or any quantum state, I should say, with itself should always be 1. Now, just to be clear, this doesn't hold for any vectors. I almost made a mistake when I said that myself. This only holds for vectors that are valid quantum states. And this is how we ensure that the probabilities will always add to 1. Now, you can work out for yourself that the left-hand side of this equation is actually equal to modulus alpha squared plus modulus beta squared, where we use this definition for psi. It's actually a fairly long calculation, so I'm not going to go through it in this lab, but all of the content we taught you in the complex numbers lab is enough to do this equation. And that's why we care about the modulus of alpha squared and the modulus of beta squared, because those are the things that actually have to add up to 1. Therefore, it makes sense to make those things probabilities. All right, let's do some quick examples before we wrap up the lab, just to get some hands-on experience with Bra-Ket notation as well as quantum probabilities. So we have a question here. Let's say that ket psi is equal to alpha times 0 plus beta times 1. And you're asked to find alpha and beta. Now, this is another Zoom poll, so I'm going to pop up the poll. And it should be asking you for the values of alpha and beta. Now, to give you some hint, I will write down the equations we had from before. The probability that psi equals 0 should be equal to alpha squared, modulus of alpha squared. The probability that psi equals 1 should be equal to the modulus of beta squared. And this table gives us both of those probabilities. So go ahead and submit your answers to this, and then I will talk about the solution in just a moment. Don't worry if you submitted by accident, these don't count. This is just for everyone to get some hands-on practice. Okay, so I'll give another 30 seconds or so before I try this problem myself. All right, so I'm going to go ahead and solve this. I already sort of started the problem by using the formulas that we had from the previous slide. So the probability that psi is 0 is equal to modulus alpha squared, and we're told from the table that that probability is 4/5. Now, if I want to find alpha, I'm just going to take the square root of both sides, and we get the modulus of alpha is equal to root 4/5. Do the same thing with beta. We know that beta squared should be 1/5. And so the modulus of beta equals square root of 1/5. So what could alpha and beta be here? Well, a lot of you said that alpha is equal to root 4/5, and beta is equal to root 1/5. And that is indeed totally a valid answer. That works. So we have ket psi equals to root 4/5 ket 0 plus root 1/5 ket 1. And that is correct. But an equally correct answer would have been to put a negative sign in front of the beta. Because when we take the modulus of beta, the negative sign disappears and we get the same probability. So this is one of those interesting things with quantum computing. We could have exactly equivalently had a state that looks like this, minus square root 1/5. Actually, I shouldn't say those two things are equal. This is just a brand new state. But these two states have the same probability of being in the state 0 or 1. So if you're measuring on a quantum computer and you want to sort of see the probabilities, these two states to you look the exact same because they have the same probabilities, even though they have different probability amplitudes. So that's just a very small example to demonstrate the difference between probability and probability amplitudes. You can have two different probability amplitudes that lead to the same probability. Okay. So, important takeaways. We are finally at the end, folks. I apologize for going so far over time. Some key takeaways. Random variables are simply possible outcomes of an experiment, where an experiment was just any process that had a random outcome. The PMF, or probability mass function, was just those plots, those bar charts. And we said that you could literally imagine the probabilities in those bars being like, chunks of metal sitting on a surface. And sometimes that helps us think about, where the balancing point is, what expectations are, etc. You can multiply probabilities together whenever you have independent events. So that's when we talked about the coin flips and the dice rolls. We introduced bra-ket notation. So kets were our column vectors, bras were our row vectors. And finally, we went over how qubit states are represented with probability amplitudes. Crucially, it's probability amplitudes, not just probabilities. And I gave a little reasoning for why that might be the case in the very last slide. Don't worry if it doesn't totally make sense right now. It will come back later and we will get more intuition. All right, so that is the end of the required content. If anybody does have questions, please feel free to throw them in the chat. I'm going to stick around and answer them. I'm also going to throw up the post-lab feedback though, just to see how everyone is feeling now with probability, bra-ket notation, all that kind of stuff. So feel free to throw any questions you have in the chat box. And I promise we are very, very close to being done for tonight. Apologies again for running over. Could I go back to the previous slide? Sure. So once again, remember, this lab session is being recorded. So you can go back and watch any of the explanations again if you'd like to. Yeah, it will be posted online. So that brings us to the end of the required content. I am going to go on to the optional content very shortly. Again, there is absolutely no obligation to stay around for that. I know we've already went quite late, but if you do have an interest in watching it later on, all of this will be uploaded to YouTube. Okay, so let's move on to the optional content. So the optional content this week is all about 2-qubit states. Now this, already you can see this is looking very similar to the die and coin example, but this time we're talking about qubits. So our possible outcomes are not rolling a 1 through 6 or flipping a heads or tails. Now it's going to be the qubit being in the state ket 0 or ket 1. And just like before, all of these 4 little cells have an equal probability of occurring. So one way to kind of think about this, although it's not a perfect analogy, is like you have 2 coins. You have coin 1 up here, coin 2 over here, and you're going to flip each of them, and each of them is going to land on heads or tails. Just like before, probabilities have to be non-negative. They have to add up to 1. And so we are going to get probabilities of 1 over 4 for all of the entries in this table. So now the question comes, how do you write the state psi? Remember, in the 1-qubit case, we wrote the state psi as a linear combination of ket 0 and ket 1, where the coefficients in that linear combination were probability amplitudes. What you'll see is that 2 qubits is fairly similar, but now instead of only having 2 possible outcomes, we have 4 possible outcomes, and we write them like this. So here we have the first qubit 0, second qubit 0, so that's the cell right there. First qubit 0, second qubit 1, so that's the cell right there. Gamma corresponds to this cell, delta corresponds to that cell. Now again, if I asked you what are alpha, beta, gamma, delta in this case, you might think the most natural thing to do is just to write their probabilities. So there is a 1/4 chance of being in the 0, 0 state, a 1/4 chance of being in the 0, 1 state, a 1/4 chance of being in the 1, 1 state, and a 1/4 chance, or sorry, 1/4 chance of being in 1, 0, and 1/4 of being in 1, 1. But just like in the previous slide, that would be incorrect because we don't write quantum states with probabilities, we write quantum states with probability amplitudes. And so in this case, we would have that the modulus squared of all the coefficients is 1/4. And so if you take the square root of that, you should see that each of the coefficients has a modulus of 1/2. And that would be the correct way to write this quantum state. Now, let's look at the PMF for this quantum state. There is a 1/4 chance of being in any of these states. And we write it like this. We write it as a linear combination of kets representing every possible outcome of all of the qubits, right? So again, if you think of the qubits as flipping coins, this is kind of like heads, 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 tails, tails, heads, and tails, tails, right? So all possibilities. And just to drive this point home again, these numbers here are probability amplitudes, not actual probabilities. So how do we get the actual probabilities that show up on this chart here? Well, you take the modulus squared of all of those probability amplitudes. So hopefully this is looking fairly similar to the 1 qubit case. It's just a slight extension. Just like when we had the coin and the die, it was fairly similar to just having the die. We just had a few extra rules. In quantum computing though, when you give yourself a second qubit like this, you can actually get some very interesting effects. So let's consider a different state now. So we're considering a different set of qubits. And suppose that their probability table, their PMF, looks like this. So there's a 1/2 chance that both qubits are 0, a 1/2 chance that both qubits are 1, and there is no chance at all that they will be 1, 0 or 0, 1. So far, so good. Oops. Giving myself away here. Anyway, so if we go ahead and write this quantum state, psi, it will be equal to some coefficient, I'll just call it alpha, times 0, 0. Now, all of the coefficients for 0, 1, and 1, 0 will just be 0, so I'm not even going to write them. We'll just have delta at the end, delta 1, 1. And if you work out what these should be, you just take the square root of the probabilities. And so one possible way to write this would be 1/√2, 0, 0, plus 1/√2, 1, 1. Just like that. Now, the really strange thing here is when you start to think of this as coins again. So let's pretend like these are 2 coins. We have coin 1 and coin 2. And what we're saying is that I'm going to flip coin 1, and let's say it lands on tails. When I flip coin 2, in this weird quantum state, it will always also land on tails. And that effect, where the state of the first qubit determines the state of the second qubit, that is called entanglement. So when you hear people talk about, quantum weirdness, we have superposition. We've learned what superposition is. We have entanglement. This is what entanglement is. When you have 2 qubits where the state of the first qubit determines what the state of the second qubit will be. And so this ket psi here is an example of an entangled state. So if we look at a PMF of an entangled state, it looks a little bit weird again, because we have some states that have no chance of happening whatsoever, right? So again, just to push this point home again, you can only ever flip 2 coins and get 2 heads or 2 tails. You can never have them be different. And that's something that does not make any sense in the real world, right? You can't have 2 coins that will always land on the same either heads or tails. This only happens in quantum mechanics, and it's one of the unique effects that gives us the power of quantum computing. So that brings us to the end of today. There are some extra problems in here. I don't think we'll go through them though. So if anybody does have questions on entanglement and 2-qubit gates, or not 2-qubit gates, 2-qubit states, feel free to ask those in the chat. When we had independent events, we multiplied. How would it be different here since they are dependent? Fantastic question. So as you were saying, these 2 events, these 2 qubits, they're no longer independent. And so it would be incorrect to multiply probabilities in this case. There is a formal way to deal with that, but what I'm going to say for now is that you should always just write out this table and circle things yourself. So if we asked you for the probability that, qubit number 2 was 1, you would just go and circle for yourself all of the cases where qubit number 2 is a 1, add them together, and that's it. Don't try and use that multiplication rule because, as you said, these are not independent. Okay, how to solve the matrices of a gate. So for anything on quantum gates and matrices, I would encourage you to watch last week's lecture and lab. I went into a lot more detail on quantum gates last week. Okay, so we are a full 30 minutes overtime. Thank you so much to the 27 of you who stuck behind to watch right until the end. As I said, though, all of this content is going to be online. So if you want to watch it again, feel free to head on over to YouTube. With that, though, I will end off today's lab. Thanks again for being a great audience, everyone. Good luck with the homework. Check on Piazza if you have any trouble at all. And yeah, have a good night. Bye, everyone.